Next up, epoxidation. So epoxidation takes an alkene and generates an epoxide from it. And this is done with a peroxy acid, which is this group I'm drawing right here. This is a generic peroxy acid. The most common one that's used almost all the time is this one. This is called metachloroperbenzoic acid, or metachloroperbenzoic acid. MCPBA is how we call it affectionately in the business. It is used pretty much standardly as this gold standard for epoxidations. All right, now let's draw the mechanism of this particular reaction. There's our group over there. So what happens here, let me draw in my lone pairs just to keep track of them. So what happens here, and what's known as the butterfly mechanism, is the pi bond will attack the oxygen, breaking this bond here. Which will then kick into here, making a pi bond here, which will now break this pi bond, which will attack that proton there. And these electrons will swing into here. And that's how you can make the epoxide. Now, let's go through that mechanism again. Let me back these arrows out and go through all the arrows again, because it's a complicated mechanism. First step, pi bond attacks the oxygen. Now, just like we saw in chlorine, the leaving group leaves. But in this case, the leaving group electrons don't just go to the atom, they go to form a bond right there. When that bond forms, this bond has to break and goes to the hydrogen that's right there. Now, the lucky thing is 1, 2, 3, 4, 5. This is a 5-member ring transition state right here. We all know that 5-member rings in chemistry are stable. So this hydrogen and this oxygen are more or less lined up. They're kind of like, I'm here and you're here, and wham, I can react with you. No problem. And now to make the bond to the other carbon, the electrons from the oxygen-hydrogen bond go there. And this is known as the butterfly mechanism, because it gives you a transition state that looks kind of like this. Make sure I get this right, guys. I'm going to go real slow to make sure I get it right. Get my carbons out here. I'm going to draw them all in a solid line just to get the atoms in. This mechanism, this transition state's a little bit weird. Not weird, but challenging. There you go. So that's the transition state right there. As you can see, it kind of resembles a butterfly if you let your mind stretch a little bit. Now, just like cyclopropane, these things can be stereospecific. Now, it can either be up or it can be down, because the approach of the MCPBA, or the per acid, can come from the top or the bottom. So they can be stereospecific. Oh, they are stereospecific. Now, let's take a look at the stereospecificity of this reaction. Let's take a look at just a standard cyclopentene. We're going to add MCPBA to this. So now, oops. So that's just a little bit bigger. All right. Put the lone pairs in because you never know. There you have it. All right. So now the pi bond attacks that oxygen. Those will loop around to here, attack that hydrogen, and those will go into there. Now, the key here is you have to understand this is a concerted mechanism, which means all of this stuff is happening simultaneously. So everything's happening at once. So there's no chance for this reaction to be occurring on two sides of the molecule at once. There's not going to be any rotation. There's no inversion. There's nothing crazy going on here. Just this molecule, this blue molecule, is coming in from the bottom or from the top, and it's going to do it 50-50. So you're going to get plus the enantiomer. Okay, so that's what happens. It's 50-50, so you can either get all top or all bottom. So these bonds can either be dashes or they can be wedges, but they can't be both. All right. Now let's look at opening of these epoxides. So let's imagine we had this epoxide right here, and we added in some acid, so H3O plus. We just added in some hydrochloric acid or something, dilute acid. From that, we're going to get this. Now, when we're looking at this mechanism and how this reaction works, I want you to think about opening the mercurium ion, opening the chlorinium ion, opening all these three-membered ring intermediates that we've been looking at. The difference between this one and the other intermediates we were working with is this isn't an intermediate. You can isolate epoxides. They're not intermediates. But they are reactive in the same way as those intermediates were. So compare them, say, for example, we saw that, and we saw this. Okay, these are all very similar. Now, they're different. I'm not saying they're the same, but they're certainly similar. So whatever reactions these can do, this one can probably do it too, especially if we make this thing positive. Like this is positive, that's positive. If we make this thing positive, it should react exactly the same as these other things. And that's what we're going to see. Let me just clear this out. So now, let's draw the back up again. So some hydronium. So you protonate the epoxide. So this is the first step. You just protonate the epoxide. Now it looks just like all the other intermediates we've been looking at. And now water, because remember we're in dilute acid, so there's tons of water in here, can come in from the side opposite and open up that epoxide. And when you do this, you get what's called a diol. But this diol, this one is going to be protonated until I deprotonate it, but you'll see. Deprotonate it to form the anti-diol. So this gives me the OH up and the OH down, the anti-diol. Anti plus the enantiomer. Plus the enantiomer. All right. That's the anti-diol. But what if, and there's always a what if, right? What if we wanted the cis diol or the syn diol? So instead of having the OHs up and down, or vice versa, we wanted them both up or both down. Of course, there's a way to do that.